Hello, this is Chuan Li from Worcester Polytechnic Institute. Thanks for the support and help from the co-authors, Guan Yimou and Dr. Li. The name of our work is Reducing and Exploring Data Augmentation Noise through Meta-Reweighting Contrastive Learning for Task Classification. The motivation of this work is that data augmentation has improved large-scale models generalization and resolving the labeling efforts. However, during the augmentation process, it will inevitably bring the noise. This is because the data augmentation assumes the augment data is label invariance, but in some cases, data augmentation will flip the label. For example, original sentence is that she looks gorgeous in her new dress. When we apply the deletion augmentation method, it will somehow delete the word gorgeous. And this will cause the model hard to identify this sentence is a positive. Thus, we propose a method to reduce and exploit the augmentation noise. The method is named MRCo, Meta-Reweight Contrastive Learning. Specifically, we utilize a Meta-Reweight to reduce the noise. It assigns large weights for low noise samples and small weights for high noise samples. We consider the contrastive learning to better representation learning for these high noise samples. So this can help us to better exploit the high noise samples without rejecting or lower the contribution of them. In our case, we consider the small weighted augmented samples as a negative samples, while the large weighted augmented samples as a positive samples. In the related work, to reduce the noise, researchers have tried the hard rejection and soft rejection. So hard rejection is to eliminate low quality augmentation methods or samples. And soft rejection is to reweight these augmented samples. So no noise samples receive large weight, high noise sample receive small weight. And to exploit the negative and positive settings, researchers tried contrastive learning. Giving a query example, minimize the distance between the positive augmented samples while maximize the distance between the negative samples. Our method combines two parts, so soft rejection and contrastive learning, to fully exploit the noise augmented samples. To re-emphasize, our work is to reduce and exploit the noise from the data augmentation. We reduce the noise through the Meta-Reweight, where the low noise samples will receive large weight, while the high noise sample will receive the small weight. The noise level are learning end-to-end from the data instead of human predefined. To exploit the noise, we utilize contrast learning, where the low-weighted augmented samples will be considered as negative keys, and high-weighted samples will be considered as positive keys. Instead of utilizing the first-in, first-out algorithm to update the negative samples queue, we propose a new in-queue DQ algorithm called lifetime-aware smallest weight algorithms, which is LASW, to update the negative queue based on samples lifetime and weight. And we will discuss the detail about these algorithms in the further slides. So in our problem definition, the training data, which are original samples D and augmented samples D hat, we consider the augmentation method as a black box. So we could apply to any kinds of augmentation method. We train a classification model based on the raw samples and the augmented samples D hat. And there comes a notation of the work. So here, X or X hat are the instance, test instance. Y and Y hat is a test label. Both uppercase X, Y are the mini match for the optimization. So our model, MRCo, contains three components: main module for feature representation learning and prediction, Meta-Reweighting module for reducing the noise, and the contrastive learning module for exploring the noise for better representation learning. The main module includes a test encoder and the classification head. It will output the loss for optimization and reweighting. The Meta-Reweight module is a shallow multi-layer perceptron. It captures the interaction between the augmented instance and its label. Specifically, it takes augmented samples hidden representation and label embedding as input. Then it will output a score from 0 to 1 to indicate the importance of the sample in the model training. The weight will be utilized, this weight will be utilized to reweight the loss from the main module. And the reweight module will only generate the weight for the augmented samples. This is because we consider the raw samples are gold without noise. Lastly, For the contrastive learning module, it's a similar size design as a main module's encoder, and we utilize the momentum rule to update the contrastive learning module. Here we consider two pairs of contrastive learning. So for the first pair, the query is a raw samples, and the positive key is a mini batch augmentation samples, and negative key are the high noise augmentations from the negative Q. And the second pairs, the query are the mini batch augmentation samples. Positive key are also the mini batch augmentation, but the representation is from the semi-size encoder inside the contrastive learning module. And the negative key is the same as previous pairs. It is also the high noise augmentation from the negative Q. The final objective function of the whole framework contains three parts: raw samples loss L, reweighted augmentation samples loss LW, and the contrastive learning loss L contrast. To control the importance of the contrastive learning, we add a hyperparameter lambda to adjust the contribution of the contrastive learning. For the simplicity and for the slides, we group raw samples loss L and reweighted augmentation loss LW into a task loss L task. Now, let's look at the detail about the last two modules. The reweight module will assign small weights for high noise samples and large weights for the no noise samples. We consider the optimization of the reweight module as a bi-level optimization. The inner optimization will optimize the main module, and the outer optimization will update the main module based on the updated main module, M star. To omit the information leakage across these heterogeneous levels of optimization, we split the mini batch of raw samples into X task and X meta, where X task is used for the inner optimization, and X meta is used for the outer optimization. Specifically, the inner optimization contains three steps. Firstly, it will utilize the mini batch of X task, Y task, and augment the mini batch X hat, Y hat to do the forward pass to get the task relevant loss. The task relevant loss, L loss, contains raw samples classification loss, L, and reweighted augmented samples loss, LW. Secondly, we do the backward pass only for the main module. To keep the connections between the main module and the meta module, we will return the backward propagation graph and gradients for the Meta-Reweighting module. This can help us to do the approximation. If we didn't do that, we somehow need the higher level gradients to update the meta module. Thirdly, we update the main module from M to M star. So this is steps for the inner step. We got the updated main module. Then move on to the outer loop. We utilize X meta and Y meta to do the forward pass to get the L meta loss. And L meta is also the classification loss like the L. Lastly, we do the backward propagation on L meta to update the Meta-Reweighting module A and reset the main module from M star to M. So this is the whole procedure to update and optimize the meta module. The motivation of contrast learning is somehow to exploit the high noise samples, because like we mentioned before, the hard rejection or soft rejection will negate the contributions of the high noise samples by providing no gradients or very small gradients for the model updates. But we want somehow to still make the negative samples contribute to the model learnings. So we're considering utilize contrast learning to learn better facial representation based on the high noise samples. Here we consider the raw samples and their relevant augmentations as query examples. And while the samples receiving the small weight as negative keys, and the raw samples and their relevant augmentations as positive keys. So, and the objective function is an NCE loss. However, there are three limitations of the existing momentum contrast learning, and we want to solve these problems with advanced contrast part. So first problem is class difference among examples are easier to learn compared with weight difference. So for each class, we will set a queue for them. In addition, the structure of negative queue to keep many negative samples is different from previous work. We make this queue priority queue with two indexes, weight from the Meta-Reweighting module and lifetime, which keep the steps of elements have stored in the queue. So the lifetime is to make the elements stored in the queue is up to date. It's not too old. Second problem is that not all augmented samples in the mini batch can be considered as a query for the contrast learning. For the augmented samples who receive small weights should not be considered as a queue. So in every mini batch, we only keep the top row of highest weighted augmented samples for contrast learning. Lastly, we design new in-queue DQ algorithm for the negative queue. In the vanilla contrast learning, they utilize first in, first out algorithm to update the negative queue. This will ignore the influence of the weight. To solve this problem, we propose a lifetime aware small weight in-queue DQ algorithm. In each training step, we will firstly replace the elements in the queue that expires lifetime requirements with small weighted elements from the mini batch. This is lifetime aware in-queue DQ. Then we will replace the elements in the queue whose weights are still larger than the rest elements in the mini batch. So this is called small weight in-queue DQ. By doing this, we can keep the elements in the queue up to date and also are low quality. After discussing the details of the model components, let's check the experiment results. We choose 7 natural language understanding tasks from glue benchmark datasets. We consider 5 easy implement accessible test augmentation methods. They are WordNet, EDA, checklist, embedding, and charts work. For the baseline method, we consider the contrast learning methods like SERT, SCL, and several variations of our approach. There are main module, which only utilizing the raw samples, main module plus AUG, which utilizing the raw samples and all augmented samples, main module and the filter, utilizing the raw samples and the filtered augmented samples. Here we utilize the readability score as a filter functions. The threshold of the readability functions are selected based on the validations dataset performance. The experiment result is listed in the table. Best performance are bold and second best are underlined. From this table, we have several observations. First, MRCo achieved the best performance across 6 of the 7 tasks on robotic-based encoder and 7 of 7 on test CNN model. On the average, MRCo achieved the best performance. Second, is compared with plain module plus AUG, which is utilizing all the augmented samples, didn't show consistent performance improvement. This could due to the noise brought by this augmentation method, while the filter function shows better performance than the plain module. This somehow indicates simple filter functions can reduce the noise from the augmented dataset. But it should be noted that our method is still better than the filter. So which means our approach to reduce and exploit the noise is much better than utilizing threshold to reject samples. Next, we show the hyperparameter analysis for the negative Q size, which is a neg, survive time slot, tau, contrast learning's importance score, lambda, and impact of positive ratio, rho. We can observe that our approach didn't need very large Q size to achieve good performance. In the relevant work, they require large Q to store the negative samples to get better performance. And the large survive time for elements stored in the negative Q is preferred. And besides this, we observe that proper contribution of the contrast learning is preferred, and a large positive ratio of mini batch for the contrast learning are good for the performance. We also did ablation study for different components of the model. From this table, we can see that each component contribute positively. So we can see that without contrast learning or without our lifetime aware small weight DQ and InQ algorithms, we can see the performance got dropped. Lastly, we want to know whether the reweight module can effectively assign the weights to the augmented samples. So we pick up 2 tasks, RTE and MRPC. Where in RTE, consider all the augmented samples at the same importance, shows better performance than the model without using any augmented samples. Well, we observed in MRPC it is contradictory. So this somehow indicates the quality of RTE's augmentation is better than the MRPC's. So in the weightoization figures, you can see that the weight of RTE is centered around 1, while for the MRPC, second most of the weights are centered around 0. So this indicates the rate module can identify the quality of the augmentation data set. So to conclude, test data augmentation will bring the noise for the downstream task. And our method can somehow reducing and exploring the noise from data augmentation. And this will improve the performance on several test classification tasks in glue benchmark dataset. And the proposed method is augmentation method agnostic. So it could be applied to other advanced augmentation method. And we also release our code in this GitHub link. If you are more interested to see the results and other additional analysis, you could see our paper